experience, or even your experiences in maybe some other science classes, you may have heard this word used before. Have we heard the word derivative?
Yes.
Yes. Do we know what it is?
Area under a curve.
That's integral. I'm going to come back to you in February. Okay? Derivative. Do we know what it is? That's okay. Maybe?
So like you said, would it be the outside of the curve?
Kind of. We're going to draw something on the outside of a curve. Yeah.
Triangle.
We're going to look at triangles for the area under a curve. We're dancing around it.
Square.
Square. We're going to use that too. We're going to use geometry shapes later this year to help us out. Okay?
Line.
We're going to draw a line. Yes. We're going to draw.
Wait, I do remember.
What is it?
Okay.
Yeah.
Hey, I think if I remember correctly, it is the slope of a certain section of a graph.
The slope of a certain line.
Yeah,
on a
certain
graph.
line going through part of the graph.
Wonderful. Where'd you learn that from? What?
We were doing the summer packet in Mainland together.
Uh-huh.
We were looking up videos on
Looking it up?
different things, and we just
You
stumbled
came across
them.
it? Good. Okay. It's probably, I'm telling you right now, the derivative concept initially might go over our head, kind of like the intermediate value theorem did when we wrote down the definition. But after we drew a picture and we talked about it, I'm hoping it starts to sink in. Okay? Again, we're going to be talking about the derivative until January. So we're going to have a lot more exposure to this. We're going to first draw a picture about what the derivative represents. Okay, so draw a first coordinate, okay, of a graph. And I want you to draw probably like half the side of a parabola going upside down. We're going to talk about two lines that we could possibly draw on this graph. One of them is what's referred to as a secant line. So we're going to define what that is. And the other one is referred to a tangent line. Maybe you've heard the word secant or tangent before. I'm pretty sure those have come up in your geometry classes when you were talking about circles and different properties or characteristics of circles. What we're going to try to do, at least from now until January, is to figure out if you were to plot a point on a curve, whatever the curve may look like, and you were to draw a line that just touches the curve at that spot. Okay, we're going to try to figure out what is the slope of that line. Okay, now this line that we drew that only touches the curve once is called a tangent line. So we're going to go ahead and define that. A line that just touches a curve at one point. Okay, I'm going to tell you again. Our goal is to figure out what is the slope of that line. Now, in your previous experience with math, how would you calculate the slope of a line? Graphically, algebraically, anything. Yeah.
One way is y equals mx plus b. The general formula for b is y-intercept. How far up it is in the y-axis.
Yep.
And then m is the actual slope.
So in the equation y equals mx plus b, m is the slope. How would you calculate the slope, though?
We calculated with rise over run.
Rise over run. Yeah.
Which you would take two different points and you would take the x values and y values.
Mm-hmm.
Now I can't remember if you put the x values on top
Okay.
or the y values on top.
Okay. So Ryan mentioned how, yeah.
X, the second x minus the first x.
Mm-hmm.
And same with the bottom. Those
Okay.
are y's, I think.
Yep. Same idea.
And it would come out as like a fraction.
As a fraction. It could be, okay? So m is the typical variable we use to represent slope, mx plus b. You can think about that as rise over run, graphically speaking. And he also mentioned something about x's and y's. Can we help him out what the formula looks like? Yeah.
Y on top, y2 minus y1 over x2 minus x1.
Perfect. Okay, so if you actually think about the phrase rise over run, rise meaning up and down like the y-axis, so your y's are up top, run meaning left and right like the x-axis, so your x's are on the bottom. Okay, so this is how we typically calculate slope. But notice how you need 2 points, correct? If you look at the y's and the x's, you need 2 of those, okay? Our issue in this question is we only know 1 point, right? The only point we know of on this line is this point that also happens to be on the curve. So this is how calculus is kind of a step up from what you've ever done before in math. Okay, because you are used to finding the slope between 2 points. What we're going to discuss this year is how can you find the slope at just 1 point. So we're going to analyze that with this little picture here. So if we're used to calculating slope between 2 points, that's where we're going to draw a secant line. A secant line is a line that connects 2 points on a curve. So in our little picture, keep in mind our goal is to figure out the slope of that black line. Okay? So keeping that point, that tangent point, would be pretty useful for us because that's the point on the line we know. Let's go ahead and pick some other point on the curve, maybe a little bit lower, and draw a line connecting those. Try to make that as straight as I could. Okay, not too good, but you get the idea. Okay, that's a straight line. So let me ask you this. We can clearly calculate the slope of the red line because we know 2 points on the red line, right? Okay, we could do rise over run, y2 minus y1, that whole bit. Okay, but would you say that the slope of the red line is pretty close to the slope of the black line? Would you say they're about the same value, or are they drastically different? They're pretty different. They're both negative, right? Don't both lines go down? Okay, but notice how the red line is much steeper than the black one. So the way that this red line is drawn right now is not the best secant line that we could have drawn if our goal is to figure out what the slope of the black line is. How do you think we should have drawn a better secant line? How could we make the red one look much closer to the black one? Because if we can figure out the slope of the red one, we could probably use that to figure out the slope of the black one. Yeah?
We know what the point is of the original, I guess, tangent line.
Mm-hmm.
And we could drop the point by like 1 in height.
A little closer. Mm-hmm.
Or like rise or drop the point in either direction.
Right.
That would essentially make a parallel line.
Perfect. So instead of having this one down here, you're saying try to pick it a little closer, right? Just drop it a little bit more.
Yeah.
Kind of?
Yeah.
Okay. We want to keep this tangent point because that's the point on the black line. Okay, we're trying to figure out the slope of the black line. So we're not going to move this one. We can, however, perhaps move this other one on the curve. Notice how if I move the red point up here and then connect those points, is the slope of that blue line closer to the black one now than what the red one was? Okay, so our goal is we're going to use a secant line because we can calculate the slope between 2 points to eventually get so close, like we're going to get this point so close to the tangent point that the secant line and the tangent line are practically the same. Do you realize how if we were to move this blue one even closer, we would get even closer to the black line?
Yeah.
Does that visually make sense? Okay, so now that that idea is sinking in, okay, let's take a look at these points a little further. We're going to take a look at that tangent point, and we're going to take a look at that other secant point that we initially drew. Okay, let's say the tangent point has some x value. We don't know what it is. It could be anything, but it has some x location. In terms of the ordered pair of the point, the x coordinate would just be x, whatever that number is. And what could we say to represent the y coordinate? What notation means the same thing as y? Yeah, f of x. Does that make sense? X comma y. We're just using function notation. Okay? So after we have this tangent point, we picked another point on the curve. We don't know what it is, but this particular point is some distance away from the tangent point. We're going to say that distance is the letter h, just to use some variable. So how might we label the x coordinate of this secant point? Yeah. X plus h. Does that make sense? We're some distance away, so we can just add that distance to get our new location. So what would the ordered pair of the secant or second point look like? The x coordinate is x plus h. What might the y coordinate look like? Yeah. F of x plus h. Very nice. All right. So this is going to lead us into the first question here. What does the expression f of x plus h minus f of x all over x plus h minus x represent? Notice how f of x plus h is the y value from one point, and you're subtracting f of x, which is the y value from the other point. Yeah. It's the slope of the secant line. Yep. Notice how we have the subtraction of the y's all divided by the subtraction of the x's, just like we said the slope formula was. Okay? So this crazy looking fraction is representing the slope of the secant line. What does this expression simplify to? We might not be able to do anything with the f of x's or whatever up top, but down below, do you see x plus h minus x? Something going to happen down there? The x's cancel. Yep. So I guess we have this kind of simplified slope to represent the slope of the secant line. Does that make sense to us? We see how it's the y's over the x's being subtracted? All right, so let's go a little bit further here. As h, okay, we said h is the distance between the x's. As that distance approaches 0, okay, as these 2 points get closer and closer and closer and closer, what happens to the secant line? What happens to the red line as these 2 points get closer and closer and closer and closer? Yeah. They become closer to equal, so these points are eventually going to be each other, which means the red line is eventually going to be what? The same line as what other line on our picture? The black line. Okay, so as the distance between the two secant points gets closer and closer and closer to 0, the secant line becomes the tangent line. So what we're going to do is we're going to bring these two questions together. Notice how we're taking the slope of the secant line and we are now merging it with this idea of a limit. Okay, the h is getting closer and closer and closer to 0. You're approaching 0. So what might this limit notation represent? If we're taking the slope of the secant line and we're letting the distance between the points eventually get so close to 0, what do you think we're finding? Yeah. The slope of the tangent line. So notice how here we said the secant line becomes the tangent line as the distance gets to 0. So therefore the slope of the secant line would eventually become the slope of the tangent line. So the slope of the tangent line. Okay? So there we go. We have some method, some algebraic mathematical method to figure out the slope of a line at one point. Something different that you guys have never done before, because you've always found the slope between 2 points. And we're specifically using limits to help us with that idea. So we're going to check out our first example here. Suppose our curve or function was that quadratic, okay, negative x squared minus 4x plus 1. We're going to find the value of this limit, okay, and this limit is representing the slope of a tangent line, okay, at any point we want. So let's go ahead and check out this limit. If you look at the first piece in the limit, okay, f of x plus h, what is that notation telling us to do? What does that mean? Think about if I said f of 3. What would you do with that 3? Yeah.
You
Plug it in
the
into all the x's. So we're going to take x plus h and plug it into all the x's in the equation. Okay, that's what the first piece represents. If you continue to look at the limit, we then have to subtract f of x, but notice how that's just the original equation that they give us. Make sure you put it in parentheses because you're subtracting the whole thing. And this is all over h. I'm not sure if this looks familiar or not, but we did a few of these in the limit unit. Remember the h's or whatever in there? Okay? I kind of slyly put those in because we're going to be doing them in this unit. Okay? So let's go ahead and expand some of these parentheses. Maybe some things will cancel out to our advantage. If you look at the first one, x plus h squared, we'd have to write it twice and go through a FOIL process. We would have x squared plus 2xh plus h squared. But if we have the negative out front, all of those would switch sign. Do I need to go through how to get those terms, or are our algebra skills up to par with that? We're okay? Okay. If we continue to go through, we can distribute the negative 4. We still have the plus 1. Next, we have to distribute in the subtraction, which is going to change all the signs. And this is all over h. There's a lot of stuff going on up top. Can we combine anything? Anything going to happen nicely to our advantage? What do you see? Yeah.
Yeah, the x squares are going to cancel.
Gone. Yep.
4x is
Gone.
gonna cancel.
Yep.
And the 1's are going to cancel.
Perfect. That was nice. So negative 2xh minus h squared minus 4h all over h. Okay, let's not lose sight of the fact that we're still evaluating a limit. Okay, h is approaching 0. And with any limit, usually we try substitution. If you were to let all the h's be 0, we would have zeros up top, 0 on the bottom. We still have some work to do. Where do you guys want to go from there? Yeah?
Can't you divide the h out of the numerator? So
Yes. Okay, so if we're going to divide all of these by h, the 1h down below, we're going to have to take an h out of every single term. So that h is gone. We have 2 h's in the middle, so we're going to lose one of those. And this last h would be gone, and those would cancel out with the 1 on the bottom. So it looks like we're left with negative 2x minus h minus 4. If we tried to plug in 0 now, yeah?
The h would just go away, so
Uh-huh.
then we have negative 2x minus 4.
Minus 4.
Because the limit does depend on where what x value we actually use.
Exactly. Notice how we have a variable left in this limit. And what that variable is telling us is no matter what x location on the graph we want, okay, what any point of focus is that we want, we can figure out the slope at that point, okay, any x value. So this expression, okay, this equation we have here is representing the slope at any point. Okay, the slope at any x value. This is what's called a derivative. Okay, the slope at any point. Coleman, you can just leave it on the side over there for now. Okay, thanks. Okay, so this is what's called a derivative, the slope at one point, the slope at any location on a graph. This concept of a derivative is so important in calculus that it gets its own notation. Do you guys see at the sentence at the bottom that little symbol F apostrophe? Okay, do you guys know how that's phrased or worded? How you say that? Yeah.
The derivative of the function f of x.
Okay, so this is called the derivative of a function. Instead of saying that every time, you can say f prime of x. Okay, but that represents the derivative of a function. Okay, the slope at any point. So in our last example, we would say f prime of x, the derivative, is negative 2x minus 4. Okay, that is the special equation, the special expression here that applies to the equation or the original equation that we started with. Okay, every equation has a different derivative because every equation has different slopes at different points. Okay, so it's not always going to be negative 2x minus 4. You're going to see how it's different practically every time. Okay, so the derivative is the slope of a tangent line, aka the slope at one point, something you haven't really done before. We're going to investigate that idea a little bit more on the back. Okay, so the result we had after we figured out that derivative limit was negative 2x minus 4. We're going to go ahead and calculate the derivative, aka slope values at these different locations. So let's say we wanted to figure out the slope of the graph at negative 4. We would simply have to plug in negative 4 into our derivative equation. And if we did that, let's see, 8 minus 4, we would get 4. Let's say we wanted to find the slope at one point, again, but that specific x location was negative 2. Based on our derivative equation, notice how the slope is 0. And if we wanted to find the slope at negative 1, looks like we would get negative 2. So we're going to see how these numbers make sense based off the graph. Like, where does the 4 come from, the 0, the negative 2, based off this picture. So this is the graph of that equation we used on the front to help us figure out the derivative. If you were to go to the x value of negative 4 on the graph, notice how you would have a height of 1. And if you were to try to draw a tangent line at that point, okay, only touching once, notice how it would be fairly steep. Okay, so we'll try to draw that in as straight as we can. Let's say we went to negative 2. On the graph, we would have a height of 5. And if we were to draw a tangent line at that point, only touching once, notice how that one would be flat. And our last x value of negative 1, height of 4, our tangent line only touching once would look something like that. So depending on where you are on the graph, the tangent line is going to look a little different. Some are steeper than others, some are positive or some are negative. Okay, it just depends on where you are graphically. Okay, so let's think about this. By investigating the graph, what does it appear that the derivative represents? Okay, we've been saying that a few times now, or at least I've said it. The derivative, okay, f prime of x, is an equation that can find the slope of the tangent line at any point on the graph of f of x. So if you were to graph the original equation, the derivative would represent the slope at any point on that original graph. Let's see if these numbers make sense. Okay, so this 4, it should be representing the slope of the tangent line at this point. If you were to look at the tangent line, does it look like that slope is 4? Could you go up 4 over 1, or even down 4 left 1, and get another point on that tangent line? Do you see how that 4 makes sense? Okay. If you look at the next point, notice how the slope is 0. And the second tangent line we drew was flat. The slope of any flat line is 0. So that one makes sense. If you look at the next one, the third tangent line we drew, if you go down 2, right 1, you have found another point on the tangent line. And notice how the slope of negative 2 checks out. So the derivative is representing the slope of a tangent line at any point. What that gives us is 2 ways to define a derivative, either mathematically or graphically. So we're going to take a look at both of those definitions. So mathematically, okay, to find the derivative, okay, how did we calculate that equation of negative 2x minus 4? Where did that come from? What did we use to find negative 2x minus 4? Let's see, we used a limit, right? And we said we wanted the h value, okay, that difference between the x's, to get really close to 0. That way the points got closer and closer and closer. And in order to figure out the slope at one point, you have to use the slope between 2 points, which we said was f of x plus h minus f of x all over h. Okay, you use the slope of a secant line and eventually get those points so close together that the secant line becomes the tangent line, aka the secant slope becomes the tangent slope. So we're going to use that limit to help us find the derivative equation. Okay? But graphically speaking, f prime of x is the slope of the tangent line at any point. So we have 2 definitions. Either the definition on how you find it, okay, mathematically, or the definition of what it represents graphically. Both are important to know, okay, how to find it and what does it mean. We doing okay so far? I know this is new to us. We've never done this, okay, but we're going to keep working at it until it really sinks in, okay? Let's go ahead and take this a little further. These 3 tangent lines we drew on the graph up here, let's go ahead and try to figure out the equations of those lines. Okay? What do you need to know to write the equation of a line? Can we think about the way some lines are written? Yeah.
2 points in a line, y-intercept.
You could know 2 points. You could know 1 point and a y-intercept. Sure. Anything else? If you think about this first line we drew here, okay, we only really knew 1 point on that line because it came from the curve. Do you know the y-intercept of that line? It's not really on our graph, right? Okay. But we also, what else do we know about this line? Not only do we know a point on the line, yeah.
We already know the slope.
We already know the slope was 4. Okay? So if you know a point and if you know a slope, we're going to use point-slope form. I know you guys are really familiar with slope-intercept, y equals mx plus b, but you're going to learn to love slope-intercept or point-slope form this year. Okay, it's going to be the one that we use practically every single time. You can turn point-slope into slope-intercept. We'll do a few of those. But we're always going to start in point-slope form. Do we remember what that looks like? Point-slope. It's kind of the crazy form of a line that no one ever remembers. Yeah.
Is it on the left side would be y minus y1
Uh-huh.
equals m
Mhm.
times x minus x1.
Yep, there we go. Okay, we're going to use point-slope form. You need to know a point and a slope to write the equation of a line. Sometimes knowing 2 points are nice, sometimes knowing a point and a y-intercept is nice, but you might not always know the y-intercept. That's why knowing any other point is useful. So let's go ahead and check this out. If we're going to write the equation of the tangent line at the -4 location at the top of your page, we have to know the point at that location, and we also have to know the slope at that location. So let's talk about the point first. If you were to plug in -4 into the original equation, okay, that parabola, what point or height value would you get out based off the graph? Can you find it based off the graph at the top? Yeah. You would get out 1. Notice how that point is on the parabola, on the curve. If you were to plug in -4 into the derivative, okay, f prime, what value did we get out there? What is the slope at that point? Yeah. 4. Okay, that came from our table. Do you notice how the notation is slightly different? The only difference is that little apostrophe. If you have that apostrophe, you're talking about a slope. If you don't have that apostrophe, you're talking about a point. 2 completely different things, and there's just one little difference between the way they look. Okay, so if we know the point and if we know the slope, we can put those together to help us write the equation of that tangent line. We would have y minus y1, which is the y value from the point, and we would need equals the slope of 4 times x minus x1, but if we subtract the x value of -4, that would change to a plus. Okay, you can leave your answer like that. That's completely okay. Do we want to turn it into slope-intercept form just because that's what we're more used to? Or are you guys okay with just leaving it the way it is? Yep, okay, so if you wanted to change it, you would have to distribute in the 4, which would leave you with 4x plus 16, but then you'd have to add the 1 over, which would make it a 17. So either one of these would be okay. They're both equations of the line that we drew, they're just in different forms. One's point slope and one is slope intercept. Okay, so either one is fine, whatever you're more comfortable with. Okay, let's try the second line we drew. Okay, the point on the curve, if we plugged in -2 into the original equation, we would have a height of 5 based off the parabola. If we plugged in -2 into the derivative, what did we say was the slope at that point? Yeah, 0. That's from our table that we did. So we got to put that information together, point slope form. We'd have y minus 5 equals 0 times x plus 2. you can leave your equation like that. Or you can change it into slope-intercept. Notice how 0 times anything on the right-hand side is still 0. So if you added over 5, you'd have y equals 5. And that makes sense graphically, right? Because we have a flat line at 5.
Yep.
Looks good. Okay, let's check out the last one. If we were to plug in -1 into the original equation to give us the point on the graph, we said we had a height of 4. And if we were to plug in -1 into the derivative to give us the slope at that point, from the table we said that was -2. So putting it all together, y minus y1 equals slope times x minus x1. You can leave it like that, or you can turn it into slope-intercept form. Y would equal -2x plus 2. Are we hanging in there? Yeah? Not at all? Going like this a little bit? We'll get there. Okay? I promise we'll get there. Can you just do me a favor for tomorrow? Okay? The derivative is the slope at any point. Okay, let's not lose that sight. And then the tangent line is the line drawn at one point. So if we merge those two statements together, the derivative is the slope of the tangent line. Okay, the slope at one point, graphically speaking. Okay? We're going to do a lot more with this tomorrow and throughout the rest of the unit. Okay?